In this example, we're going to use the OMAR web interface. In particular, we're going to start from the search page where you have a list of results. I'm going to show the use of a position quality evaluator, which shows you the positional quality of a point that's been dropped on a raw image. Right now I have the ICONUS image. ICONUS has built-in CLEs within the RPC models that we propagate. So we'll go ahead and click on an ICONUS. Let's go ahead and just zoom in somewhere. Keep zooming. And on this page, this is what we call the raw image space page. So the pixels are shown as they are, but you can add some type of filtering to it, like some histogram stretching with viewport or global or brightness contrast, different types of interpolation techniques. You can rotate the buildings so that they're up, so they all are lined up. You can go north or reset back to the original image. In this case, what I'd like to show you is the position quality evaluator. This is a drop point, so if we take this point and we drop it on the map somewhere, this point will change. Well, if you have an area where we have a lot of elevation, this is like 1 kilometer post spacing, so there's not going to be much variation. But as you drop, you get different error calculations. The error calculations will show up over here on the left-hand side that you see over here. And you got general information about this point that you just dropped down here. So you got what we're reading as height above the ellipsoid and height above mean sea level. The actual center point for this point. Let's change it to decimal degrees. If you want decimal degrees, or you can go to MGRS representation. But in any case, what we'd like to know is how accurate this point is when we drop it onto the map. And we show you the actual DTED. The DTED that I have is actually a DTED 0. I don't know why it's called RTEDx. But it's a DTED cell. It's a 1 kilometer post spacing, not very accurate. So you get a very large circle. You have more accurate elevation, so then your circle should diminish in size and get a better error. Over here, you'll see that the circular error, or the horizontal error that you see here, it has a radial measurement of about 29.6 meters. So somewhere horizontally, this point that you see here is somewhere within roughly about 30 meters of the point that we just dropped. So the actual lat long that you see here is accurate within like 30 meters of 90% probability. We can decrease the probability and say I just want 50%, and the circle will go down. So I'm 50% confident that the point lies within this general area. You can go up to 90%, or you can say 95%. And your confidence level increases, your circle size or your circular error is going to increase. Let's go back down to 90%. Also, the second measurement, which is your linear error. So if I say that this point is around 34.7 meters above the ellipsoid, we're within 26 meters of being accurate. So it's somewhere between 34.7 and plus or minus 26 meters of that value. The other information is just assuming major and minor axes, radial distances, and the azimuth of which you see this circle is turned of 27.4 degrees along the major axis. And you can click anywhere, and if you have higher terrain detail, like if you're over areas which start to have mountainous regions and you have a very accurate terrain model, this circular error will increase and decrease based on where it's being dropped. And that concludes the example of the position quality evaluator.